In this homework problem, we're being asked to evaluate an integral in spherical coordinates, and this integral is given to us currently in rectangular coordinates, and we're being told to evaluate over the unit ball centered at the origin. In rectangular coordinates, that would be x squared plus y squared plus z squared equals 1. One of the ways that you know, just when you first look at a problem, that you might want to consider using spherical coordinates is because we see the x squared plus y squared plus z squared. Any surface whose formula has this piece as a component will be really easy to convert to spherical coordinates. And that's because rho squared is equal to x squared plus y squared plus z squared. So also remember, in spherical coordinates, rho measures the distance of a point from the origin. So it can go out in any direction. So let's say we want to know the coordinates for this point. Rho represents that straight line distance. Spherical coordinates have rho, theta, and phi. The theta in spherical coordinates is exactly the same as the theta in polar and cylindrical coordinates. It measures the angle around just specifically the xy plane. So we would have to project this point down onto the xy plane and measure the angle of the projection to get theta. So because theta represents the angle in the xy plane, we have the option to potentially go 0 to 360 or 0 to 2 pi. So when working with theta, we can go, let's do this in radians. We typically do these in radians, 0 to 2 pi. And I mention that because when it comes time to work with phi, phi represents the angle with the z-axis, the positive z-axis. So if we're lined up with the positive z-axis, we want to know what angle we need to come down to meet that line we would draw that represents rho. The distance represents rho. So technically, phi only needs to vary from 0 to pi, or 0 to 180 degrees. If we wanted to go back further, we would just use theta to take us around to that side of our three-dimensional space. So phi never needs to go past pi or 180 degrees. And that's really important to understand and to know when you're working on these integrals. So a full sphere, this one in particular, has a formula or an equation of x squared plus y squared plus z squared equals 1. But we know x squared plus y squared plus z squared is equal to rho squared. So if we do this swap of this entire expression and replace it with rho squared, we can get our limits for rho. So we would have, instead of x squared plus y squared plus z squared equals 1, we would have rho squared equals 1. And when we take the square root of both sides, we don't have to do a plus or minus. In the process of converting this equation to spherical coordinates, nowhere has phi or theta come about in the formula. And what that means is that there are no restrictions on phi or theta. So, and this is a good thing to remember for math in general. If a variable is missing from your equation, that just means there's no restrictions on it. All an equation is telling you a restriction that you must follow. So the fact that the phi and the theta are missing in this equation means that there's no restrictions, and we're going to use their full domain. We are integrating over a unit ball, and since we're integrating over a volume, we're going all the way from the center of the ball out to the edge of the ball. So if you want to think of this as having a radius of 1. If we're integrating over the entire volume, that means the points that we're using can be anywhere from the origin out to the edge of the ball. And the origin is just 0. So to rewrite this integral in terms of spherical coordinates, the typical order that we would integrate is d rho, d phi, d theta. Our rho is going to vary from 0 to 1. That's because we're using this entire sphere. So we can go from the center all the way out to the edge, which has an equation of rho equals 1. And we're using the entire sphere. So phi can go all the way from 0 to pi, and theta can go all the way from 0 to 2 pi. That would represent the entire sphere of radius 1 and all of the volume inside of it. So the integration part has been converted. We need to also convert our integrand. And again, I see x squared plus y squared plus z squared. So another great clue to tell me that I need to use spherical coordinates. So we know that x squared plus y squared plus z squared can be replaced with rho squared. So I'm going to do that here. And instead of x squared plus y squared plus z squared to the 9/2 power, we know that x squared plus y squared plus z squared is equal to rho squared. And when we multiply those powers together, we get p to the 9th. But that's not our entire integrand. Anytime you do a conversion, there's also an additional part that must always be included when you're converting from rectangular to spherical. If you're the one doing the converting, then you must also include rho squared sine phi. That is the extra integrating factor that allows us to just change dx, dy, dz into d rho, d phi, d theta. This is our magic piece that makes those equivalent. So if we simplify this just a little, we'll be ready to integrate. We've got the integral from 0 to 2 pi, the integral from 0 to pi, and the integral from 0 to 1 of rho to the 11th power sine phi. And we're going to start by integrating with respect to rho, and then phi, and then theta. So we're going to start at the innermost integral, and it's with respect to rho. So rho is the only variable that we're going to integrate. So here's the rho, and it's a power, so we're just going to do power rule on it. The other integrals, just leave them be. We haven't started those yet. We're just working on the stuff inside those orange brackets. So the integral of rho to the 11th with respect to rho is going to be 1/12 rho to the 12th. And sine phi stays because it's like a coefficient. Since this is multiplication in between them, that's technically a coefficient. And we want to evaluate this from 0 to 1. And remember, this was with respect to rho, so these values are being plugged into rho. When we evaluate our antiderivative at 1, we get 1/12 sine phi. When we evaluate at 0, we get 0. And then subtracting gives us a new integrand of 1/12 sine phi. And now we're ready to move on to the next most inner integration, which is the d phi. So we want to look for a phi in the integrand, which is right here. So we're having to find the antiderivative of sine phi, and that is negative cosine phi. And the 1/12 is just going to get carried along because it's a coefficient. and we want to evaluate this from 0 to pi. If we plug in pi, the cosine of pi is -1. Cosine of pi is -1, so we're left with -1/12 times -1, which is +1/12. If we plug in 0, the cosine of 0 is equal to +1 times a -1/12 is going to give us a -1/12, and we always subtract in between these two values when we're evaluating an integral. So that means our final integrand for our last integration we need to do with respect to theta is going to be a 12 minus a -12, which is really plus a 12, so 2/12 or a sixth. So now we've got integral from 0 to 2 pi of 1/6 d theta. Well, this time we're integrating with respect to theta. There is no thetas there, just a constant. And the rule for any constant is antiderivative for a constant is a linear function with that particular variable. Integrate from 0 to 2 pi. We're going to have a sixth times 2 pi, which is pi over 3. Plug in 0, we get 0, so we're going to be subtracting nothing. So our final answer is pi over 3.